Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Here begins the essay, the year 1973, a pivotal juncture in the ongoing human quest to comprehend the cosmos. It witnessed the publication of a groundbreaking work, a trinity of intertwined efforts that would ultimately redefine our capacity to perceive the universe's hidden symphony. The authors, a partnership of intellectual brilliance, were Barish, Weiss, and Thorne. The subject gravitational waves. To grasp the genesis of this singular undertaking, we must first consider the intellectual antecedents that provided its foundation. The concept of gravitational waves, ripples in the fabric of spacetime itself, originated with the genius of Albert Einstein. Einstein, in his 1916 theory of general relativity, posited that accelerated masses would generate these waves, propagating outwards at the speed of light, a fundamental prediction directly arising from his radical reimagining of gravity. However, the challenges of detecting these ephemeral disturbances were, at that time, monumental. Einstein himself, for a period, questioned the observability of such subtle phenomena, a testament to the technological hurdles that then stood in. The early theoretical groundwork, however, was immensely crucial. It established the framework, the mathematical language, the conceptual landscape. Works like the one by H. Bondi, which explored the energy carried by gravitational waves, and the subsequent contributions by Peter Bergman and Felix Pirani, which refined the understanding of their properties and their interaction with matter, were essential components. These investigations laid the groundwork for the advanced theoretical structure later employed in this particular work, which took the original Einstein conjecture and began the arduous task of devising ways to detect them. The immediate predecessor to the work in question was the intellectual drive to move theoretical considerations into the practical realm. The endeavour involved the meticulous calibration of sophisticated instruments capable of detecting minute disturbances in spacetime. Central to this effort was the establishment of sensitive detectors, devices engineered to measure the minuscule changes caused by the passage of gravitational waves. A key figure in this evolution was Joseph Weber, whose pioneering experiments in the 1960s, using resonant bar detectors, were the initial, though ultimately inconclusive, attempt to directly observe these elusive waves. Weber's work, even if the results were not replicated, stimulated an invigorated pursuit of detection methods. It galvanized the scientific community and highlighted the need for more sensitive and refined instrumentation. The contribution by Barish, Weiss, and Thorne in 1973, therefore, represented a vital step forward from Weber's initial efforts. The work itself involved a confluence of theoretical innovation and practical engineering. It was not a single paper, but rather the collective work of several connected strands of research, each addressing a component of the problem. At its core, it laid out the foundational concepts and designs for what would become the laser interferometer gravitational wave detectors, a revolutionary technology later realized at the Laser Interferometer Gravitational Wave Observatory, or LI. The design principles proposed in 1973 were predicated on the notion of using laser interferometry to measure the tiny changes in the distance between two mirrors, separated by a considerable baseline. The passage of a gravitational wave would subtly stretch and compress spacetime, causing a differential displacement of these mirrors. The work elucidated the theoretical underpinnings of these displacements, describing how gravitational waves with a specific frequency and amplitude would affect the light beams traveling between them. The intellectual bedrock of their approach involved a keen understanding of precision measurement. The paper, or rather, the suite of research it represented, delved into the details of optical interferometry, the physics of lasers, and the challenges of isolating the detector from external disturbances such as seismic vibrations and thermal noise. It investigated the use of hyperlasers to maximize signal strength and explored techniques to minimize the impact of noise inherent in the measurement process. Weiss, in particular, laid out the critical optical configuration the Michelson interferometer modified for detecting gravitational waves. It involved splitting a laser beam and sending the beams along two orthogonal arms, kilometers in length. The beams would then recombine, and the amount of light that was interfered with would be measured. The work carefully detailed the anticipated magnitude of the signal, the expected sensitivity of the detector, and the challenges involved in isolating the detector from environmental noise. They introduced the concept of the power spectral density, that is, the distribution of noise over a spectrum of frequencies, offering strategies to mitigate the consequences of particular noise sources. Thorne, theoretical physicist, contributed mathematical and conceptual frameworks. His work on the theory of gravitational waves was essential for understanding the expected signatures of astrophysical events, such as the collision of black holes, on the LIGO detectors. Thorne's contributions extended to the development of methods to analyze the data, extract the signal, and infer the properties of the source of gravitational waves. His engagement was, therefore, integral to understanding the theoretical significance. Barish, as a leader in the construction of the scientific instruments, oversaw the realization of their concepts. The work, therefore, did not merely rest on theoretical constructs, it was a blueprint for a tangible, functioning apparatus. The papers, the designs, the blueprints for the LIGO project were a product of many collaborators. The impact of the work in the immediate aftermath was primarily to set a roadmap for progress. It spurred further research and development in the field. It facilitated the formation of collaborations and the allocation of resources to build the first effective detectors. However, any immediate, quantifiable data coming directly from the work, alone, was impossible, as the detectors would take decades to be put into operation. The work of 1973 did not receive immediate, widespread recognition. The concepts were complex and the technological challenges were immense. It was a long-term endeavour, a patient investment in the future of astrophysics. The initial reception was primarily among those deeply familiar with gravitational wave physics and those undertaking the task of detector development. The subsequent impact of this work, however, is colossal. It provided the foundational theoretical concepts, the technical designs, and the essential engineering solutions that would lead to the realization of the LIGO detectors. These detectors, now supplemented by the Virgo detector in Italy, have transformed our understanding of the LIGO experiment, which has realized the ambition expressed in 1973, has been used to directly observe gravitational waves from a plethora of sources, including binary black hole mergers, neutron star mergers, and the in-spiral of compact objects. This work has opened an entirely new window onto the cosmos, allowing us to probe the most extreme environments in the universe and test the predictions of general relativity with unprecedented precision. The work did not proceed in a vacuum. Several influences shaped its development. Einstein's theoretical work, as previously stated, was the initial inspiration. Weber's experiments provided a critical stimulus to the field. The contributions by Thorne's collaboration on theoretical modelling and Weiss engineering insights were critical parts of the overall undertaking. The influences flowing from the work have also been immense. It has facilitated an entire field of study. It has transformed the way we study the universe. It has led to a new generation of physicists and engineers who are now pushing the boundaries of gravitational wave astronomy. It has provided direct access to the most energetic and dynamic events in the cosmos, including the mergers of black holes. The direct detection of gravitational waves has confirmed key predictions of general relativity and provided insight into the behavior of matter under extreme conditions. The work led to the 2017 Nobel Prize in Physics, illustrating its profound impact. The work's significance continues to evolve. Subsequent refinements of the LIGO detectors, along with advancements in data analysis techniques, are constantly improving the sensitivity, which will allow the detection of fainter signals and consequently see further events. The ongoing development of the gravitational wave network, including the planned construction of future generation detectors, is expanding the reach of gravitational wave astronomy. There have also been critiques. Initial criticisms centered on the technical challenges of detector construction and the potential for instrumental noise to obscure the signals. As detector technology advanced, these critiques were largely addressed because the signal was then confirmed. In conclusion, the 1973 work of Barish, Weiss, and Thorne stands as a testament to the power of human intellect. It was a monumental step in the evolution of gravitational wave astronomy. It was born of deep theoretical insight and the application of pioneering engineering. It has ushered in a new era of exploration and transformed our understanding of space and time. This work is a remarkable example of how scientific imagination, coupled with rigorous, focused execution, can reshape our comprehension of the universe and its fundamental laws. The legacy continues to grow, promising further discoveries.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.